Hello, this is Malachi Bishop, and this is our C750 Rehabilitation Counseling Research and Program Evaluation. We've been discussing parametric and non-parametric tests and tests of difference. Today we're going to look at tests of relationship, a couple in particular. We are going to be talking about the correlation coefficient and tests of relationships such as the Pearson R, and then we'll also be looking at tests of multiple relationships such as multiple regression. We won't be looking at these others, but other examples include canonical correlation, cluster analysis, factor analysis, discriminant analysis, path analysis, and structural equation modeling. In correlational studies, the goal is to investigate the strength of a relationship between variables, or the extent to which variables vary together. Or you can think of it as the extent to which variation in one variable corresponds to variation in one or more other variables. In bivariate correlation, which means correlation between two variables, the correlation statistics involve the calculation of a correlation coefficient, or R, and the correlation coefficient ranges from -1 to +1. An R of 1 represents a perfect positive correlation, and the size of R tells us the magnitude of the relationship. So in your reading of the literature, you will see various R's, and if you're wondering how to interpret those, Guilford in 1956 suggested that one way of interpreting R is as follows. If R is less than 20, then you have a slight, almost negligible relationship. 20 to 40 would be a low correlation. There's a definite but very small relationship. 40 to 70 would be a moderate correlation, a substantial relationship, and then 70 to 90 a high correlation or marked relationship, and over 90, an R of over 90 would be a very high correlation, very dependable relationship. Another suggested interpretation of R would be 10 to 30 is weak, 30 to 60 is moderate, 60 to 90 is strong, and as we said, R of 1 means a perfect relationship, and R of 0 means no relationship. To give you a sense of what this looks like graphically, I'm using an interactive correlation website here. Right now we're looking at a relationship between the data that are graphed here of 0. If, however, we look at increasing correlations, that would be a correlation of R equals 10.1 or 10, 20, and you see now we're starting to see the beginning of a more visible relationship as we get into a correlation of 0.4, 0.5, R of 0.5, 0.6, and now we're getting into very strong relationships, and 0.9, we have a very definite relationship, and then we said 1 is a perfect relationship with a -1 correlation coefficient would look like that. So the idea here is, if you have a perfect relationship, as this variable on the x-axis is, let's say, 1, then this variable on the y-axis, measured on the y-axis, would correlate perfectly, so it would also be 1. And as the values on the x-axis increase, the values on the y-axis would increase correspondingly. So you have a perfect correlation here. Perfect negative correlation as the values on the x-axis increase, the values on the y-axis decrease. So something you can find and play with online. Just search for interactive correlation coefficient, and you'll be able to find there are a number of those available online. Let's look at multiple regression then. Multiple regression is like correlation. It's a correlational technique, and it provides us information about the relationship between a dependent variable, and in multiple regression we call that a criterion variable, and two or more predictor variables or independent variables. So in multiple regression we call the independent variables predictors and the dependent variables criterion variable. So multiple regression can be used to predict or determine causation, or to see what independent predictor variables contribute to a dependent criterion variable. So it's an extension of bivariate analysis. Talk about three concepts. Again, this is fairly complicated analysis, and I'm going to try and keep it on the conceptual level and help you just to understand some of these concepts. The line of best fit, the relationship between R and R squared, and capital R and capital R squared, and that has to do with the relationship between correlation coefficient and these multiple regression correlation coefficients that we'll talk about, and then the F statistic and what that means in multiple regression. So the idea of the line of best fit, or the line of least squares. Let's talk about that and look at some visual examples of how that works. Once your line of best fit has been determined, it allows prediction of one score from another. That is, as long as we know one score on one variable, we can predict the score on another. And this is how that works. If we have data on two variables, m and n, so let's say height and weight. Looks like m would be weight, and n is height in some sort of unit, we don't know. But it doesn't matter what they are. These are two variables, and we have data for 4 people, John, Pete, Sally, and Myra. Alright, now if we plot the data for John with the 70 on the m and 7 on the n scale, whatever that is, and for John, Pete, Sally, and Myra, if we plot that in a graph, then it would look something like this. See how nicely the data lined up, very neatly correlated there. For this example, that's a good thing. We'll make it a little more complicated in a second. But if we plotted the data for John, Pete, Sally, and Myra on a graph, and that we could draw a line right through them here, and we'll call this the line of best fit, and I'll tell you why in a minute. But the idea is, once we have this line of best fit, if I have data on another person, so now we're joined by a 5th person, we'll call her Jane, and we know one score for Jane. We know that Jane has an n of 10. Alright, so she's a 10 on the n variable. If we know Jane is a 10 on the n variable, then if we plot her on our line of best fit, right at the 10 for the n variable, then we can go over to the m variable, the corresponding point on our line of best fit, and see, make an estimate that she's probably going to be around a 90 on the m variable. In other words, we can predict, knowing just one variable, where a person will lie on the other variable if the data line up really nicely like this. This line would be a really good way to predict scores. In reality, though, the data aren't that neat. They spread out a lot more, and this is still pretty well-aligned data. It's usually not this neat, but if the scores for another group of people were distributed this way, and we wanted to draw our line of best fit, we would draw the line of best fit, and you notice it's not touching any of the points. Sometimes it is, sometimes it's not. What the line of best fit is a mathematical calculation of a line where, if you took into account all the data points, the distances between the data points and the line are the smallest they can be. So it has to do with finding the smallest distance between the data point, each data point, and a line that can be drawn to represent the data. Now if the data looked like this, and we had Jane came back and she had an N on this scale, and we had our line of best fit, we could find out for Jane, we could make a we could plot her on the line of best fit at the 10, and we could make an estimate of where she would be on the M. But because the correlation isn't quite so nice, there's some difference between the points here, and those would represent some potential error. Some we wouldn't be quite so sure that our estimate was as good as if as when the data lined up so neatly. So there's some variability in this line of best fit. So we can still estimate fairly well where Jane would fall using this line based on her N variable, but we couldn't be sure that we didn't have some error in our prediction. We can describe this line in terms of a mathematical equation that some of you are probably familiar with. It's called the regression equation, and you may have seen it as y equals bx plus a, or you may have seen it as y equals mx plus b, where y is the predicted value of y. So that's what we don't know. B is the slope, or the amount of change that results in y with a change in 1 unit of x. So b represents the slope of the line. In other words, as x increases or decreases by 1 unit, y would increase or decrease by b units. X is the value of the x variable that we do know, and then a is the intercept, which is a constant amount. Its corresponding points along the y variable differ from points along the x variable by some constant amount, which we call the intercept, and a. So based on that equation, let's go back and look at it again. Y equals bx plus a. We can calculate the value of y, or Jane's score on the M scale, based on her score on the N scale, x, and the slope of the line, and the intercept, some constant amount. So using that equation, we can predict the value of one variable, for example height, by knowing the value of another. In multiple regression, what happens is we're able to add independent variables and assess their additional contribution to the criterion variable. So instead of just predicting a person's weight based on their height, we can predict their person's weight based on their height and their age, and you can throw in a whole lot of other variables. So in multiple regression, we can look at multiple independent variables, or predictor variables. Now note that the b value in that equation, called the regression coefficient, in multiple regression, when these values are standardized, they are called beta with a capital B, and they tell the relative importance of each variable. So if you see in a table in a multiple regression analysis article, you'll see a table with a beta value, and you look at the beta values, right? If one beta is bigger than another, it tells you that that variable, that predictor variable, is relatively more important than the predictor variable with the smaller beta. So it's contributing a little more to the prediction if it has a bigger, larger beta value. You can say it's more important to the prediction. So using this equation, researchers can calculate and make predictions about such questions as which clients will be the most likely to have a successful outcome in voc rehab. And you can use multiple predictors, such as age, gender, education level, and so on. And based on that combination of predictors, you can see which are the most important predictors in whether a person has a more or less successful outcome in their vocational rehabilitation. So it's a very useful statistical method. So we talk about the correlation coefficient R, small r, and the capital R and the R squared. In multiple regression, capital R is called the multiple correlation coefficient. Just like R, small r, the correlation coefficient, it tells you about the relationship between variables. But whereas small r tells you about the relationship between two variables, the capital R multiple correlation coefficient tells you about the relationship between the criterion variable and a combination of predictor variables. So it's the relationship between one and multiple variables. And just like small r correlation coefficient, the capital R multiple correlation coefficient ranges on a scale from 0 to 1. An interesting thing happens if you square R, capital R, you'll see R squared. You'll see that in multiple regression and other regression analyses. It's called the coefficient of multiple determination. And what R square is it represents the amount of variance, how much variance there is in the criterion variable that is explained by the variance in all the combined predictor variables. In other words, it tells you how well the variables that you're using to predict something actually do predict that thing. So a higher R squared means that you're predicting more, that your variables that you have selected are better predictors, and a low R squared means that they are not predicting much of the variance. So they're not they're not being very effective predictors. If R squared equals 0.50, then your combination of predictor variables are explaining about half of the variance. All the other variance is accounted for by other unidentified factors that are not included in your study or not included in your set of predictors. Then finally, you will also see the F statistic. And in multiple regression, we use the F statistic. If the F statistic is statistically significant, that means that the predictors or independent variables do predict some acceptable amount of the variance in the dependent variable. So you will see in an article, you see a statement like this. Results of the forward stepwise multiple regression. And forward stepwise refers to the way in which the predictor variables were entered. And they can be entered a number of ways. They can be entered all at once, or they can be entered in steps based on the research that is being done. So that just describes different approaches to entering the variables into the equation. So forward stepwise multiple regression of 6 variables of interest on quality of life. So we're looking at, this was actually a study I did where I was predicting with some other researchers, we were predicting quality of life, and we were trying to see how much 6 other variables contributed to or predicted quality of life. And this was an epilepsy sample, and we were looking at general health, social support, mental health. So we had measures for all of those things. So we had variables for those. We also had how often a person had a seizure frequency. And then we also had employment, and then how much the person's seizures were interfering with their daily life. So we had 6 variables, and we wanted to see how well they predicted quality of life and which predicted more importantly. The regression analysis produced a significant result. So that means our F statistic is going to be significant. And if you look at F and the degrees of freedom, 4 and 102 equals 91.67, and the P is significant. P is less than 0.001. So we have a significant result, and then we also know that the R squared is 0.782, and that means quite a bit of the variance in quality of life was explained by our 4 of our 6 variables anyway. So an R-squared of 78 is quite high. That's quite a bit of variance in the quality of life. And general health, social support, mental health, and seizure frequency were found to be important predictors. The other 2 variables, employment status and seizure interference, were not found to make a significant contribution. So the beta for those 2 variables, you would see a beta that was very low because they were not important predictors of quality of life. If you looked at the beta of general health, social support, mental health, and seizure frequency, those would be larger. And so you could look at the betas for those different variables and see which was the most important predictor, which of those 4 variables contributed the most to the prediction of quality of life. That's an overview of multiple regression. And I think that concludes our discussion of the inferential statistics until we look at how to do some of these statistics using statistical software.